get back to where we ended. Is that the AC? Ah, the mic. Hello? Hello? Okay. Is that the AC? Can you turn it off? No. Oh, thank you. Good. All right, remember that we were trying to solve this problem. We had these two black holes, two compact objects of some size r going about and emitting gravitational waves. And when we learned the first time, and also maybe you got this, now I just have to look in this direction. If you sit over there, then they will I'm going to do this and get the impression that there is more people, you guys. So also in the colloquium, how we're going to set up this problem when you have a separation of scales. And remember, we wrote an action in which we're going to take our theory, in which there is some UV physics or short distance physics. And since we are looking, there's a probe, you can call it lambda bar if you want, which in this case will be the companion. So this case R, this could be anything. The theory will describe any perturbation of an object which is long wavelength. So we constructed this point particle action, which has the usual mass, which also accounts for the binding, as we said. There's a spin part, which I'm not going to talk much about. And then we had these other terms. And let me just write one of them. And then if we do it this way, and just to be consistent, so there's an integral in d tau, there's a mass, there's the spin, and there's this quadruple deformation. What we said last time is that if you're dealing with a black hole, for example, then you can split this quadruple deformation into two pieces. One which exists there in the background of the short modes, which means, for example, if this object was already, say, spinning, and therefore, if it's spinning, you will have a quadruple moment which is proportional to the square of the spin. And therefore, this could have a non-zero background on the short modes. And then the short modes. So all the physics here gives you some quadruple moment, which does not depend on the existence of the perturbation. It's just a property of the object. And then there is also, it doesn't have to be an average, but there is a response which is, if you think about this theory, remember it's a word line, right? So I can put here a delta function localized on the word line and make everything space-time. So we can remember this term here. We have a square root of GVV, d sigma, and then we can have a delta function over like the position of the particle, and then we just add the d for x. And then this is localized on the wall. But the point here, the important point, is that there is an external perturbation, and reacted to that external perturbation, I get a response. And one thing I said last time is that this response, in principle, is a Whole-Green's function, because it's not obvious that necessarily you have to be diagonal. You can parameterize the properties of this Green's function based on the symmetries, because it's an expectation value of the Qs. And then I talk about the love numbers, but one thing that I was reminded is that this could be frequency dependent. And this function will start with something in the omega goes to 0 limit. Well, the limit in which omega goes to 0, and that's the static response. And that's the love number is the static response. So if you parameterize this with some coefficients, some function, after you work out the symmetries, there will be a response function depending on omega, and then you have a constant, plus, in principle, they could have some imaginary part, plus something omega squared, blah, 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 blah. And constants will give me what I wrote last time as the response, which is, I forgot how I call it, but some like CE-EIJ. This is a number, and this is the love number, which is in the static limit. Then there is some absorption properties because the response could be imaginary. And then one thing that I don't remember if I said, but let me say now, is that there could be higher derivative terms. So even though this vanishes for black holes, when I plug this back in here, then this term, if I look at the conservative parts, which are even in velocity, in frequency, omega minus omega invariant, so this, omega 4, and so on, there will be an E squared term, but there will also be an E dot squared term. This term here, this is love. This is 0 for black holes. This guy here, I don't think he has a name, but it's not necessarily 0. The moment you put dots, right, the ringing of the black hole, because it absorbs, will produce a non-zero quadrupole deformation. Whereas in the static limit, that thing goes away. Yeah. Yes? I haven't talked about the binary yet. I'm just saying I have some blob of matter, and I'm treating that blob of matter as a point particle. Now, this will describe the black holes, the neutron stars, whichever compact object we have, and that's what I'm talking about love, because I'm talking about the properties of that object. Number one. Number two, when I have a binary, then this background here, which I told you, for example, for a spinning black hole will be S squared, will be the quadrupole moment of the binary. And then the response will be if I put the binary in an external field, which is something which I'm not doing, right? So right now I'm talking, for example, about a black hole. And if you have a black hole, then the quadrupole will be some spin-dependent term, often going like proportional to the spin square, just even in tensor is the only thing that you can write down. And there will be a response. This coupling means that if I turn on E, I get a response for Q. And that's all I'm doing. I'm just calculating in linear response theory. What is the value of Q when I turn on E? And obviously it would be proportional to E. And if I replace that in my action, I get an operator that goes like E squared. This is 0 for no external fields, unlike this guy, which is not 0 when I turn the field off. In other words, this coupling, if I put a spin square, will contribute to the one-point function. So it will contribute to the metric. And the curve metric will have these terms. If you don't include these terms, you don't get the curve metric. This guy does not contribute, thanks to Birkhoff theorem, to the one-point function. It contributes to the two-point function. You need to perturb the guy to be able to create a one-point function. And that's indeed, this very compact expression summarizes a lot of information that often goes by complicated names and theorems, like Birkhoff theorem. The fact that just the mass and the spin describes a black hole It's basically these two light degrees of freedom, right? The position and the rotation. Then you get the heavy modes. And this guy gives you the love number, which cannot enter in the solution, because we know that mass and spin determine the one-point function, but they do enter if you turn on an electric field, curvature. Now, this is 0 for black holes, but it's not 0. This guy is not 0, and actually this starts at 6 post-Newtonian order, and this starts at 5th post-Newtonian order. Last. No, her. No, but this is something else. What I just said is something else. If there was a coefficient here, right, and this coefficient will enter in the one-point function, then we will violate Birkhoff's theorem. But this, even if the black hole was, if the love number was not 0, it will not enter in the one-point function anyway, because it goes like E squared. So the Birkhoff theorem does not forbid you from having a love, because this number will not enter in the solution. Basically, what this is saying is that once you start writing terms which are quadratic in the field, everything goes. Birkhoff does not restrict you anymore. Very good. So this is true in GR and in 4 dimensions, but it's not true in general. And this logic we can use also for the binary, and this is what we stopped last time. It's like, who is this guy? For the case of the binary. Because I'm going to use exactly the same theory. The difference will be is that in the case of the black holes, I care a lot about this guy, because this is the guy that's giving me the response of the compact objects that will eventually enter in the waveform. For the case of the binary, these effects are there, by the way. I cannot just say that this is 0. If I now plug this back in here, so this gives me 2 terms. One term gives you get an E squared, as I wrote over there, because you just put the response bar, and another thing which will be the guy that is inherent to the binary, which is the one that we need to match. The same way that we match the mass, remember, looking at the one-point function far away, we need to provide a matching for this guy, which I'll tell you in a minute. But this guy could be there as well for the binary. In fact, if I look at the binary, I have to keep this term. Why? Because this deformation of the binary could also be induced by the radiation itself. So in principle, there will be terms in the theory which will be quadratic in the radiation, and those terms will also contribute here. And therefore, in fact, they enter a higher order, but at some point you will have to include them. And maybe for people who have looked at this before, it's because you can always write terms like this with the E square will definitely contribute. But we are not interested in this right now. We want to know who this guy is for the case of the binary, because now we just writing this theory for the body, we control everything. We control that there is a mass, there is a spin, and there is a bunch of coefficients that describe the black hole, say. The love number is 0, but this guy is not 0. There is absorption that I don't have a lot of time to explain how it goes, but there is also ways to introduce and describe this guy, which is when we pack this back in here, we're separating the scales. We're saying essentially that this is long, we're looking at long distance, and it's decoupling from the short distance, decoupling from the long distance, and we plug it back into the action. It's also conservative. The DESY party part is a little bit more complicated because it's long-lived. There is no decoupling in time, remember. These functions are time-dependent. And therefore, I had to be a little bit more careful how do I describe the fact that these functions of time have Green's functions that also have imaginary parts. but I'm not going to get into this right now. What I want to tell you is, if you ignore black hole absorption, this theory is all you need. And now we put two of these guys in a binary. And what we need to know is who this guy is, because in this theory, remember, we can compute, for example, a one-point function. And this one-point function, as we did for the matching of the mass, has a 0-0 component that we look far away, Schwarzschild, and this matches the M. But it also has an ij component that will come from here. This guy, this eij, has a term which goes like this. Sorry, ij, 0-0. And therefore, if I'm looking for the hij out of this Feynman rule, I'm going to get this guy, and therefore this is going to be proportional to two derivatives of qij. And this is just the box. And then it's the retarded time. And the whole point is that once I know this guy, which will be proportional to this guy, I can go ahead and compute the flux, and then I get the energy. Or if you want to be fancier, you can compute an amplitude. This will have two frequencies, so you can get an omega square, omega to the 4. There will be a measure. That measure will give you another factor of omega, because it will have d3k over 2k. I don't want to write a lot because I'm going to show you in a second. And then you get another k, so you get 5 omegas, but that's an amplitude. You want an energy, so you multiply the energy by the k mu, or omega, you get 6. And then you get omega qq to the 6, and that's exactly the same as this being, or equal, since we all know it, minus q over 5, q triple dot, ij. And this is symmetric trace-free because this guy is symmetric and trace-free. Do that as an exercise. Go from this theory, compute the one-point function, find this energy flux. The other way is what I was telling you, which you can do as well. There's an emission from this qij. Then you compute an amplitude, ij. There is some tensorial structure that you're emitting with some k. Do this as an exercise and tell me if it doesn't work, we can do it offline as well. There will be an amplitude omega contracted with epsilon. You square it. There will be a measure. I'm just writing what I said I was not going to do. And that'll give you a rate multiplied by the energy, and then you recover this. Okay? So all of this is just to say that once you know the Q, we're in good shape because we can get this, right? The Q of the binary. And if we know M, the M of the binary now will be the energy. And this will be the flux. So if I know the energy and the flux, then I can construct the gravitational wave phase in the adiabatic approximation, in which you need to track omega dot, say for a circular orbit. Because remember, as I said, I don't remember if in the colloquium or what, this, the orbital frequency times a factor of 2 will give you the gravitational wave frequency on the quadrupolar linear leading amplitude approximation. And if I know this, I know this. And how do I know this? Well, I know E of omega, and I know E dot of omega, and then I trade for omega dot. I integrate this guy, and I get the phase. Good question. I'm going to do averages. I'm not going to really track because I'm looking at the energy integrated over a period. That's essentially saying that the E dot over E is a small number, that it doesn't change much. The scale of radiation reaction is much shorter, it's much longer, sorry, than the period. It's in fact 2.5 V5, right? The radiation reaction scale. So you can just say that you are on a circular conservative, because if we look at the binding energy, we don't see the flux, but we say, okay, this is conservative when we are losing energy because of the emission, and then we just average over a period. We don't have to do that, by the way. We can compute the exact, I don't have time to explain, but you can ask me, I can compute the exact radiation reaction force, I can compute the exact flux, and if I average, I get precisely this, because the force itself goes like to the phi. And then you do xv, and you get the q1, you integrate by parts, and you get 3.3. So we can do this if we want, and then take average to do this. If you find the solution, you might find that the transients, because it's not really shrinking into adiabatic orbits, but this is good enough, at least towards the end, because the split of the time scale of radiation reaction is small. Okay, so this is basically a very crash course on how do we construct the waveforms. Well, we know this Q, and from our field theory point of view, we just need to know who these Qs are. That's what this effective field theory will give you. Will give you the M, which I haven't told you how to match yet, because the M of the black hole and Schwarzschild we can do just by looking at the far away. The M of the binary, the binding energy, we can also do the exact same way. But it's sometimes convenient just to compute it without turning on this guy. Because here, in this coupling, we can get the M again, the same way, right? MH00, like we did before. But there's another piece which is easier, 1. So we can match the M with the 1. Essentially, if we just turn completely vacuum radiation. That will be computing the binding energy of the system without the radiation, rather than look at how the binding energy sources the static part of this field, which is the 0,0 component, right? And that will be also, once we see how we match this Q, you will see also how we can match the M if we wanted to through exactly the same procedure. Because ultimately, what we're going to do is get the T mu or the pseudo T mu of the system. And then we're going to do moments of this guy and moments of this guy, so integrals of this guy over this XL will be XI1, XIL. Some moments of these guys are going to give us all this, well, depends on the indices. I'll show you. Here I'm being very sketchy because there are indices here and indices here, right? All the moments will be moments of this T mu. That's going to be our matching condition, and all we have to do then is tell me who this guy is. But once you know who this guy is, that you can do by the matching, then you get all the Qs by just doing these integrals. And you will see that doing these integrals is actually very easy because doing these integrals are moments of t. Moments of t in Fourier space are very easy to calculate. So then you just go to Fourier space and expand, and then you get all these moments for free. You will see in a minute. But why did I tell you this now? It's just to say that I don't have to be very creative to tell you that we can get the energy. From the coupling of the 0,0 component. Now, we don't do it this way. We could do it this way, and it will be exactly the same, but it's much easier to match the 1 than it is to match the MH00, because obviously MH00 will come from the coupling to the T00, right? So what's the logic here? The logic here is like completely generic. We have a blob of matter. We look at it from far away, and it looks like a point. It has some binding energy, it has some rotational degrees of freedom, and it has some moments. some multiple moments. Those moments could be intrinsic, if you have, for example, a spinning black hole, or a binary system, or it could be response, like the tidal responses. When we go to the binary, which is what we care, we want to compute this guy also. I mean, you can think of this as a background of the short modes for the binary energy, okay? So now the question is, how do we do that? How do we get these Qs? And this will be our strategy. Our strategy will be very generic. We just say we have, again, a blob of matter and couples to some external gravitational field. And the key here will be to define the linear, so the full action of GR, right? So we have the Einstein-Hilbert action. And we're going to say, well, there are modes that live in here, as I was saying before. Remember, this will be the short modes. I'm going to give them a name because it's going to be convenient. I'm going to call them big H. And therefore, when I expand this, and if I say, oh, those guys vary on scales which have to do with my system. And what is the scale of the binary? Well, the scale of the binary is 1 over R. So I'm going to have these guys short modes. That the scale, remember, space, right, with the scale of the systems. Those guys are often also called potentials. These are the binding modes. When I open this up, then not only the matter T mu nu will couple to this guy. So obviously, I'm going to have a matter H mu nu coupling in my action. But I will also have from here, if I say that my metric is, we are in the perturbative regime, so we're going to span around Minkowski. And then we said that this metric, we have a perturbation, and that perturbation can have two modes. I'm going to call this one bar, which is the radiation modes, and I'm going to call this ones big H, which are my binding modes. These ones are the ones that live far away. So these are the ones that they are on shell. And these are the ones that are off shell, because the spatial part, remember, there is no decoupling in time. Everything scales with V in time scale. So the spatial part will be much varying on much shorter scales than the time. The time will be longer. So these are quasi-static modes. So the D0, which is the same for everybody, is V over R. And this guy, since it's on shell, so the D0 and the DI for this guy is both V over R. So these modes are V over R, V over R. And these modes are V over R, 1 over R. And there's as we'll see a little bit, there's a formal way to understand this in terms of the modes of the field. But it's also very intuitive that whatever is happening in here is sourcing what's happening out there, and they decouple. For the most part. I mean, this decoupling will fail at some point because of these tails, but I'm not going to get into the details now. But what it means is, I mean, somebody might say, but what the heck is this, right? I mean, you have an action. This action will give you a quadratic piece, which we just make it this guy. And then I'm going to have h cube, da, da, da. So h d squared, h squared, h squared, da, 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 da. This is what you learn maybe in GR or in field theory, so there is a cubic coupling there. There is a propagator. There's a Feynman rule here, which goes like k squared from the derivative. And this is what a field series will do, right? You have an action, you expand it, and you have couplings in some weak field approximation. So what am I doing? What I'm doing is like saying, well, in all of these diagrams that I'm going to end up when I compute my, as I told you in the colloquium, right, my whole path integral that accounts for everything that will give me the entire solution to the problem, which is very hard to do, although we later will get to these guys in the post-Minkowskian approximation. But what I'm doing to that very complicated, in principle complicated integral is separated into these regions because I know that some of those modes of the gravitational field will be responsible for the binding. Some of the modes are going to be radiation. And I can do that here, and then I can have now these potential modes. They're going to have like a different propagator. It's going to be p squared, because the p zeros are going to be subleading, so I'm going to treat them perturbatively. So I'm going to start adding them. I'm going to have a p zero squared here, but I'm going to start expanding. So I'm going to put it as an expansion. So the green function of these potential modes will be static plus corrections that depend on p0. But this p0, if you now go and do the e to the ikx of the propagator, if you go to space, then the p0, since they are now upstairs, they are analytic. Why do you have a force which is long range? The long range behavior of a force comes because it's a non-analytic green function, right? Otherwise, you will never get a 1 over r, you will get a bunch of contact terms. We make it contact in time by putting the p0s up. And therefore, this trades into derivatives, and derivatives of the e to the I p0 will be a delta function. You integrate that by parts, and then you hit the x's that are going to be everywhere, you get v's. So this guy will scale like v squared. We make it analytic in time by expanding these guys up. It's still non-analytic in p, so we get the 1 over r's. Better be, otherwise it will get delta functions, interactions, which we don't want, right? We want long-range forces, right? Again, one of the beauties that you don't appreciate until much later, right, about how these green functions work and why the analytic properties of the green functions and the behavior of the forces and so on is deeply connected. What if I don't give you the chance? Yes. No, please, go ahead. Yes. I'm not sure I follow. This approximation that we do has to do with the fact that this ratio of scales is correct. When this breaks down, then this expansion fails. When does this break down, you might say? Well, if you're getting very close, then the separation will no longer be so much longer than the radius. The gravitational wave emission will not be so much separated than little r because the velocities are close to 1. And then this whole thing breaks down. That's not at a given post-Newtonian order. That's where the whole picture is wrong. There is no Pn order at which this goes wrong. The series itself, we don't even know the convergence of the series, right? So, the big R. That's different. When does the big R enter in the waveform far away in the post-Newtonian regime will be proportional to when R enters, which will be a ratio of scales with R, because it's a phase, so it has to be dimensionless. We did a matching last time, and we found that this coefficient C scales like R to the 5th for the black hole, so, which happens to be 0, but I mean the dimensionless ratio would have been R over R to the 5th, and because this is ordered GM over R is V squared to the 5th, that would be V10. That's what I said last time. But that's another thing. This has nothing to do with breaking down. This has to do with at which order in the perturbative expansion the effects of the tidal deformability enter in the waveform. Even very early on, even with V is 10 to the minus 100, this will be the effect. You cannot measure it. You can only see it with V is closer to 1. And then you might ask, well, but what about higher corrections, how accurate you can be? So it's a trade-off. The perturbative expansion is correct, so you still have control, but you can see very minute corrections, right? So what am I doing here? I'm doing something that if I was strong enough, I wouldn't need to do, which is split this full Green's function. But because we are not, and also because it's very convenient to split the problem in pieces because of the separation of scales, we're going to do this slaughtering of the Green's function. I'm going to get the full propagator of this guy split into this infinite series because each one of them is going to cost me a velocity. And then I'm good because I'm in a post-Newtonian approximation. If I wasn't in a post-Newtonian approximation, I couldn't do this. If the V was order 1, this is not correct. I mean, it's correct, it's just that you have to keep going, right? I mean, you could, in fact, I think someone did this, try to resum this, but it's not the smartest thing to do. Because as I told you in the colloquium also, we can compute the PM angles now very accurately, just taking the full Green's function, right? Yeah, well, not now, but yeah, yes. Yeah, my idea is to get to, my problem here is that you don't appreciate what we're doing in the other case if you haven't seen this first. And that's why I always spend some time, not as much as I should, but giving you the flavor of what it has been done for the last 20 years with modern EFT ideas. And then we get into more modern next week. Right? I'm sure Ricardo has shown some flavors of this to many of you guys already. But it's nice to refresh your mind before we start with the other stuff. And since I have 2 weeks, I can do this. Very good. So then when we go here, then you see you're going to have coupling. So then you have the full propagator for the other guy, right? Let's put the P0 square. But then what happens is clear that here, we're going to get, from this type of couplings in my action, we're going to get H, H, H. We're going to get things like this. And these are all short, so they're all living here. So that means that when I couple to this H mu nu, a linear order in the radiation, this T will not only be matter, it will also be these guys. And therefore, if I take this action plus matter, and who is matter? This guy. That guy has a T mu nu, but that's not the end of the story, because this also produces a contribution to my T mu nu. And therefore, a linear order, I'm going to get a coupling to this T mu nu, and if I was careful, I would have put here the Plancks, and that would be my coupling. A linear order, the blob not only couples matter, it also couples these guys. Which I'm integrating out the same way that I integrated out all the short scales that go into this theory for the black hole or the neutron star. I'm also going to integrate out these guys. What is the difference? The difference is that for the case of the neutron star, nobody can do that analytically. We don't even know what the love number of a neutron star is. There are theories, there are values, ranges, and so on when you do the matching, even the mass. Hard to say. Here, I don't have the same level of difficulty. This is much easier. I know the theory. I can do this exactly, right? I can compute M exactly for the binary. I can compute the Q exactly because I know who this T mu nu is. Modulo my uncertainties. Where are the uncertainties? Well, at some point, this guy will enter, and this I don't know. So it will appear at the end in this calculation. In this calculation of the flux, there will be inside here some love for you. And that's what we're going to see in the data, right? It came all the way from the point particle, right? For example, in the binding energy. Okay, so my goal will be then to construct this guy. And I'm doing space-time now. And remember flat. Remember, I mean, I was doing this in curved space, but then I span around flat space. I could do self-force and span around a background, but I'm not doing that. This is flat. This is the flat measure. But why am I integrating d4x here while I was doing d taus over there? Because here, this guy has T matter, which is localized on the world lines. But it also has the self-energy, the self-gravitating part. I don't know, maybe that's not a nice word. The binding forces, binding potentials that are localized on the binary scale. Which is R. This is the points of the wall line. This is the binary. So that's why I keep the X in here. Because now it's not localized on this thing, it's localized on these scales. At the end, though, we're going to get stuff that will be localized on the wall lines and the potentials. It will be functions of X and 1 over R's, right? Yeah. I mean, we do to some extent, yeah. No, of course it's not a gravity problem. I mean, it's QCD problem, right? So if you take QCD under high pressure, and then you want to see, actually, I don't know to what extent this is under control. I mean, there are different assumptions that one can make about the equation of states of the neutron star, and then get from there like a size, a mass, and so. I have no idea how this is done. But there is a lot of uncertainties there, and that's why we get this out of the data within some range, and that will give you, if you see a counterpart that you know, for example, it's a neutron star, it will tell you more or less the values that you will expect neutron stars to be, which is between 1 and 3, I think, or 2 and 3. Good question. Will be seen maybe by Lisa, right? Yeah, I think, well, ground-based, correct me if I'm wrong, Ricardo, but I don't think we're going to see white dwarfs. No, exactly. Lisa might see them. As a background, as a stochastic background, maybe white dwarfs be seen by Lisa. Yeah. In which case, the lobe effects are not that important, right? So good. We want to extract this guy. How are we going to do that? And also, how do I go from this to this here with my QE coupling? So that's our goal. So first, how do we go from this theory of T's, of T minus? What theory of T minus? How do we go from the T minus to the Q's? It's not a stretch of imagination to realize that moments of T minus are going to give me these Q's. You just need to do a little bit of group theory to figure out exactly how. So the point is that we have the binary, and this we describe with potentials and radiation. We describe the coupling, the linear coupling to radiation with this T mu nu. Whereas in the effective theory, we have something else, which is the tau, if you want, you can leave for the matching at least at this order, the only thing that matters. You can say that you're arresting the binary with the same time. The center of mass of the binary is not moving, so that's time. How do we go from here to here? And this also, usually. And then dot, 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 right? I mean, this has the Q's. Then there is a coupling that sometimes is written with J, which is the electric component of the mass quadrupole, and then there's the current that couples to the magnetic part. This guy is sometimes with -4/3 for historical reasons. And then derivatives of this guy will couple to the octopole, and then you have higher J's and so on. So dot, dot, dot is because here you're going to have a coupling, for example, with the octopole to a derivative of this guy, symmetric trace-free. So higher derivatives are going to give me now a d cube. So there is a derivative expansion in which now I have another x, right? There is another index that will scale with the size. So this will have 3 sizes, another derivative. The derivatives are derivatives of this guy, which is lambda. So there will be naturally here an expansion in R over lambda at some given order. So each one of these terms will give me another Pn order, because this will be V to some order. And because in the flux, you often get squares, and this guys don't interfere, then you get Q square, octuple square, next one square, and so on, so another V square. Figuring out who these guys are then becomes the whole shebang, because then just squaring this, either through the one-point function as I did before, or through the amplitude that you're going to do as an exercise, you're going to get an E dot that will have the Q triple dot square. Oof. Is it 16 over 45? I think. J. Oh, 189, Ricardo? 4. The octuple. Da, da, da. Okay? This theory predicts this. All I need to know is who these guys are and who the dots are. And for the dots, I need the binding, because the binding will tell me the energy, how the things move. And if I know how the things move, and I know the formula for the E dot, and I have the formula for E, I get the phase. So now I need to first know how the Q's and the T's are related. Step 1. Step 2, I need to calculate the T's. And what I do is, well, I match. I treat this as a point particle. What does that mean? Well, that means that I sit here somewhere, conveniently in the center of mass. So this guy is going to be a function of x. But I'm going to expand it near the center of mass. Big X, x minus x. And I'm going to go to the center of mass, so I'm going to set this to 0. And dot, 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 dot. Why am I allowed to do that? In fact, you're not allowed to do that. We're going to do it anyway. because these D's are derivatives of the radiation field that scale with lambda. These x's are going to be integrated in the binary, which scale with r. Therefore, this will be a controlled derivative expansion, provided these h's do stay in there. When you have tails, you have the problem, and some of these h's start like getting into where they shouldn't be, and you have to be a little bit more careful. Luckily, as long as you use so-called dimensional regularization, you're fine. The stuff that is bad will be divergences that you can deal with. But you have to be careful. We are not going to discuss this now. We're just going to be pragmatic. And therefore, this is going to be fine. I have to say, though, that the way that people do this in other approaches, they have issues with defining things properly in the regions, near zone, far zone, etc. For us, luckily, DIMREG does a lot of decoupling for us, which is very nice. Yeah. No, these people came before us, right? I mean, these calculations have been done, as I said in the colloquium, right? From, if you want, from Dorste, and then Einstein and Hoffman in 35, and then Chandrasekhar, I think, around in the 70s, and then in the 90s, Blanchet Damour, then in the 2000, Goldberger, Rostin, myself, Ricardo, and so on, started to creep in, and now a bunch of people. But this comes from a long history, right? Strict proof. Nothing here is strict. Like Feynman will say, if you want more rigor, go to the mathematicians. We're in a physics lecture. Rigor for what in particular? No, if we disagree, somebody made a mistake. Huh? At least one of the two made a mistake, yes. So far, I think we forgot things, but we have not made mistakes. And I can tell you what we forgot, that once we fixed, it was okay. Many times people thought that what we were doing was wrong, but it's not that it's wrong, it's just that it's a little more subtle, but this story of the tails we did first, by the way. In fact, Luke learned how to do it because he knew the right answer from us. Right? That is not to say that what they have done is amazing. I find it remarkable that doing it in the old-fashioned way, these guys can compute things correctly, right? It's really, it's an amazing group of people, young people included, not just Luc Blanchet, obviously. But okay, so we do this. And I lost a little bit of track what I wanted to say. That then we put it here. Because remember, we want to match. So we go in the regime of overlap. So then what do we get? We get our first term, and as I said, I can match however I want, so I'm going to match with the ij component. If I was doing the 0, 0, I would get the energy, obviously. And why am I doing that? Because this guy has space and time. And this guy, after I do this, the first term doesn't have anything. It just have an h of t. And I put my center of mass at the origin. Plus, xk d3x dt. Here. And so on. I can take this one out, and then I get integrals of the t. For example, tij d3x times hij t0 dt. This is good. That's the dt. That's exactly what I want because it starts to look like my guy, dt. So now I just need to massage this guy to get my coupling. My coupling looks like QE. This does not yet look like QE. And why do I want to write the QE, you might say? Because it's simplifying my life. I know what the long distance physics is because it's restrained by symmetries. And therefore, if I do that, then I just have to square these guys to get a flux. If you start from here, you can still do it, but then you might need more terms because they can talk to each other. This has 3 indices. This has 2 indices after I did my group theory reduction, as we'll see, that this transforms under rotations like a quadrupole, this is an octupole, and so on. Here, I haven't done that reduction yet. And that's what I need to do, that's all. And I start with this guy. So who is this guy? So now, I'm going to use some tricks. Let me emphasize that I don't have to do this. You can always do this. You can always go here, call this whatever you want to call it. Call this guy, I don't know, Sij, and it couples to Hij. And that's one of the couplings in your theory. But you just need more. This is what you emit when you compute a flux. So you might as well compute this guy. There's nothing wrong with it. Why we do that is because we think that that simplifies your life, because you disentangle many of the cross terms that you get. Okay, so then we need to deal with this guy, and I'm going to use the trick that this guy is conserved. So this is called the Ward identity, if you want. There's a little bit of cheating here. I'm in linearized gravity. So for the linearized gravity part, I can use this. Because the T mu of the whole thing, that the guy who is conserved is the whole T mu that also includes this guy. But there's the nonlinearities of this guy that I'm not including. Because in fact, you have to be careful that this M also depends on time. Well, first, because I can. But second, because usually if you have an amplitude associated with the emission, that will come from the T mu H mu coupling, right? When I wrote QE and I told you the amplitude was like Q, I'm actually just doing the usual Tij amplitude, right? And then if you have an amplitude, or if you want the full amplitude, and you do something like this, often this goes by the name of Ward identity. So that's why this is the Ward. What does it do? What it does is that in reality, we have the whole guy, but the properties of the amplitude just get the longitudinal and the temporal components out. So you don't get the unphysical modes radiating, which you don't want. I mean, you can. Again, this is also a gauge issue, right? There's a lot of freedom, There are a lot of gauge issues here that you have to be careful. I don't want to get too much in detail about. But you could propagate things that ultimately cancel, and it's completely fine. If you do everything consistently, the answer has to be the same. That's usually what happens if you have the K mu and mu amplitude. With photons, essentially, the word then say if you replace the epsilon by K, you get 0. And why? Because then if you go to a photon, this is 1, 0, 0, 1, and then the K0 and the K, they are the same, and that means that the A0 and the AC cancel, so the temporal and longitudinal are gone. And you just get the transverse guys, right? Now the question that you might ask, how is the word identity? This is the subtle point that I don't want to get into. Why is the word identity or the conservation law true, which is often associated with symmetries, like gauge invariance or global invariance as well, when we have to fix a gauge to do a calculation, right? There's a whole story about BRST symmetries that guarantee that the answers are gauge invariant, though we're breaking the gauge invariance to do the calculation. In this way, the way that this works, that why am I allowed to do this, is because when I compute and I get rid of all the potential modes, actually I have to be very careful, because I need to add a gauge fixing term to be able to do calculations. When I wrote for you I over P squared, nobody said, well, what's up here? There's this whole P mu alpha beta tensor, right, from HH, propagate. How do you get this guy if you don't fix a gauge? You have to fix a gauge to be able to invert the box. And if you choose a gauge, then you're destroying the symmetry, so you put a gauge fixing term. What guarantees you then that this is going to be true? Well, you do it in a way in which when you gauge fix and you're going to get rid of the guys which are short, I'm going to integrate over the short guys. I'm going to make it such that it still respects the symmetries of the long distance. So if I had a derivative, I'm going to make it a covariant derivative with respect to this guy of the H that I'm removing. And that will be why this is true. If you don't do that, you get the wrong answers. So you have to use the background field gauge, and that's very important. It turns out that it doesn't matter until very high order, but at some point it does matter, and you get the wrong answer otherwise. So those are a little bit of subtleties, which have to do with how you remove these guys from your theory, how we do the matching for that theory, which I haven't told you yet, because I haven't yet told you how to get the Q's from the T's. But we're almost there, right? Because do this as an exercise, otherwise I'm going to waste too much time. To prove using this property, which you can say 0 and ij, and then you start with the 0 and the I, and then integrate by parts. Assuming, and here comes also the parts which are tricky, that you can throw away the boundary terms, but let's not get into that. That this guy can be written as this. And that's the integration by parts. When you do the DIs, you hit these guys. And then you hit the other guy when you integrate by parts. And then you can show that this is equal to this using this. Between the ij component, the 0 component, right? Because this is a mu. And you have to use it twice. These are sometimes called moment relations. Which again, if you don't use this gauge, which you don't have to, then don't use this, keep this guy, and compute with this guy. No problem. You complicate your life, but it's up to you. Because this is subtle, actually, right? That you have to be careful with your gauge fixing, to use relations that include the fact that you're computing also nonlinear gravitational interactions. This is clean. It's more work, maybe, but it's clean. You're not doing anything wrong for sure. But if you're careful, you can simplify your life, and this is very nice because now it's almost trivial, because now we can identify our guy directly. We go back here, we rewrite this now as a half. Well, this is 0 is time. I don't know if I call it anymore. But we have the integral over time that we want to do. That's the whole point. So we have the T00 xi xj d3x, which is an object on its own. And there are derivatives. But since there is a dt, I can put those derivatives into the hij by integrated by parts using this dt. And then I get dt. That's what the zeros, dt. And now I look, that starts to look like this. Because there are many components in this E. And one of the components is precisely hij 0, 0. Then it has I0, J0, da, 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 da. But this is the guy that we're getting. If you do the other components, I'm doing the hij, but I can do the other components, I would have gotten the other terms. Yes? Oh, it will, yes. Yeah. That's a very good question. The question is that I'm a little bit cheating. When I call this radiation, there are still regions of this far zone that include long potentials. They are sourced by this guy. And that's what I was telling you that I didn't do, which is I can do the matching of the T00 for the mass. I was going to do it here. We sometimes do it with the 1, but we can also do it with the H00. And that's the guy that will source radiation, will also talk to my M, and also to the L. Yeah? That's why I'm saying these are my short potentials. But that's also a little tricky because, I mean, what is the long potential really? Because this M also contains M1 and M2, which are also sourcing potentials. I'm separating the things that is like the 1-point function that is going to talk to the radiation and the binding that is between those two. It so happened to be the same guy, right? Because the 1, because of different variants, right? The 1 and the H00 are related. And then this is my guy, and that even takes care of the half and the sign if I didn't spoil it, because there was a minus in both. So this makes it our Qij. And I should not do it this way. I should remind myself that it's this guy. So then Qij is equal the integral of Tij, sorry, T00, xi, xj. Yeah, plus dot, dot, dot. And what I mean by dot, 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 because this was our first. Then we have to go to this guy, and we have to do it to this guy, and so on. So then we need to reduce another guy, which is Tij sk, and this has a 2 and a 1. So you also get a 3. But you can have other components. So when you reduce these guys, remove the traces, essentially. So the object with the honest 3 indices without the traces will go into the octuple, but then you start taking traces of higher order x's, which you're going to get, and all those traces are going to renormalize the lower order guys. And then you use your moment relations to trade all the things, And then you get corrections here. For example, you get a term which goes like TII plus TII. Then you start getting something like T0I xi dot or T00 dot dot x square. Everything times xi xj. So all of this times xi xj, which is symmetric trace-free, so this is symmetric trace-free. Plus these guys. And dot, dot, dot. So now there are two things here that we learn. We learn that there is a derivative expansion, and at each order in the derivative expansion, I get new terms. So they will be down by post-Newtonian corrections because the derivative expansion is in R over lambda. So there will be R over lambda corrections. Each one of these terms will cost me R over lambda because they come from higher order guys, right? But on top of that, each one of these guys, which I haven't told you how we compute, and that will be the last part, themselves will cost me V, but from the short distance, which is the binary. There will be GM over R and B squared. So if I want to be accurate, I have to match. First, figure out up to what order I need this derivative expansion, and then up to what order I need each one of these T's, such that I get the quadrupole. Then if I need to go to higher orders, I need the quadrupole, then I can also get this guy, I can also get this guy, to the NPN order that you need. I have to tell you how to match this. But once you learn how to match this, then this is done. The only thing you need to know afterwards is how you take these dots. And for that, we need the binding, which will be the same than matching for this guy. Matching for this guy will also give us the binding because, as you can easily see by doing the 0, 0, the integral of T0, 0 will give you the energy. And from the energy, you can get the equations of motion because it gives you the potential, and the potential gives you the forces. So last stop for us will be how do we get these T's? And now comes the matching at a deeper level. Now we open the binary. We have those two wall lines, these two M2 theta 1, theta 2, 1 and 2. And all my potentials. And this whole thing will produce both the H00, but I can also match the 1 by ignoring it and computing just the vacuum amplitude, or I compute the 1-point function. What does that include? Well, that includes radiation from the binary, these guys themselves. And a leading order, this will obviously give me a T mu, which is M1 plus M2, localized, so clearly the leading order Q will be MXX sum over the particles. Do that as an exercise. But then also, we're going to get things like this, which also contribute. And here you have a K1, a K2, and a K. And the point is that this K is on shell, this K is off shell, the full momentum, the K0 is much smaller. So here you get K, let's call it K, and let's call it L, K, and L plus K. So you just do the matching, right? You compute this diagram, you compute whatever, when you strip off this leg, whatever you get is the T mu. So you're going to get something that depends if you go to mixed Fourier space in T and K. You get it in space or in full momentum, but it's very convenient to do this mixed thing. in which you Fourier transform just on x. Why? Because, see, I start bringing the case down when I expand, and I start getting k dot x to the L. Take the case outside, k to the L. These are the moments that I want. So by getting an expansion of this guy in k, I start getting the moments that I need. And that also has to take care of these guys, because this guy is not scaling homogeneously. It gets an L, which scales like 1 over r, but it gets an L plus k, which k scales like v over r. So you need to expand this guy in k. When you expand this guy in k, you're going to get higher L's, and then you do that integral. And when you do that integral, those k's will tell you that you will also have to expand that k, and it will also contribute to the moment from this diagram. The same from this guy and so on. You do that, and you're going to get now that the T00, for example, will not only be the masses, but it will also give you the GM over R. That will come from doing this for the 0, 0. And those GM over R will also then enter in renormalizing the quadrupole. There will also be kinetic terms because there will be V-square couplings here. So this quadrupole is going to start getting corrections, mass, binding energy, kinetic, and potentials, and that will cost you Pn. So the matching of this guy will cost you Pn. Each order of these guys will cost me Pn. The 0, 0, if you want, will give you the binding, but you can also do the binding by doing diagrams in which literally you just don't put anything, and then you just get the 1. That will give you the binding. You get that, and you get the potentials from which you get the equations of motion. You do this, and you get the fluxes, that then you take dots using the equations of motion, and then you compute as far as you can go. And where are we right now? We are at 4 Pn. I have to say, with standard tools, they're at 4 Pn. With our tools, we are at 4 Pn for the potential part, and we very recently finished the TPM for the radiation complete. But with our tools, we're also at 5 Pn for the bindings, and I say potential is binding potential, not just the potentials. The tails are also here, so if you want potential, plant there. The 5 Pn we are completing from the binding from the EFT side, but here the 4 Pn is known only with the standard tools. The 3 Pn was recently done, but not the 4 Pn. There are a lot of subtleties that we will encounter on the way, which are, for example, these tails. This is not the end of the story. What I just told you is correct. Modulo the nonlinear interactions in the far zone, which means that when I told you I could compute the 1-point function and I got this square, I was kind of cheating because this guy can also talk to the mass. And when I compute the 1-point function, I should include also these diagrams. So I have to square these diagrams too to compute the fluxes. And they will also enter when I compute, for example, the vacuum energy to compute the binding. So I also have to include those guys. I have to be careful on how we include these guys in the binding and how we include these guys in the fluxes. This also starts getting very interesting because this, for example, has UV divergences. And at some point in this iteration, at 4 Pn, we start seeing infrared divergences. And these infrared divergences and these UV divergences are connected because at the end we get also logarithms. So there's a beautiful story about logarithms. I don't have time to explain, but they will reappear, hopefully, if we have time in the PM version. And they have to do with the way we split things. Because we are saying that the radiations and the potentials are separate, the fact that there is an infrared divergence in a potential means that this potential didn't want to stay here. It wanted to go out. Because remember that I told you I was expanding in P0 over P's. At some point, I put too many P's downstairs. And that will give me IR divergence in an integral over D3P. And that's bad. But here, I did a derivative expansion. So, which meant that I brought the case down. This derivative expansion is this e to the I kx down. So I put the case up. I get UV divergences. So putting the case up in the numerators through the multiple expansions will give me UV divergences. Putting the piece down through potential expansion of quasi-instantaneous with my IR divergences, but they're actually related. If I had done the full thing, I would not see this. But I will get logs. And that's like the lamp shift. And that's what we'll see in PM, that we don't have that problem. It will be translated into something else. And we will directly get these logarithms, which are not the same as the log of x that I told you in the lecture. They are log of v, velocity. Okay? You plug the machine, you put everything in, you're very careful about the regions, you're very careful about your regulators because you're going to run into all kind of divergences. You put it all together. Very recently, for example, we finished this, and this we control very well. The state of the art is just 1 PN away from us. And this is in PN. In PM, we have done even more. But in PN, this is where we are right now. So next time, I'm going to talk about scattering, how it connects to this story, what are the new ideas, the new tools that we're using to do these calculations. I haven't told you much about how these integrals are done, but you can easily see what type of integrals you get. You get static, 1/p², three-dimensional integrals with many iterated Green's functions of 1/p². These are understood up to 5 loops. There's a bit of an interesting story here. There's a bit of decoupling that you can do because the integrals that you need at 5 PN and odd PN are the same that you need at even PN. And therefore, you get all the master integrals for free. And that's why the 5 PN was completed, knowing the master integrals that were computed by a collaboration with Ricardo and Stefano and Pier Paolo, and I forgot who else, to do these master integrals. It so happened that also in the standard approach, the integral can be done in coordinate space. And they knew the answer, while Pier Paolo had to fit numerically this, right, which was very impressive. But the integrals that we can do in post-Minkowskian, I mean, so far I think we are the only ones. We and the amplitude community is the only one that has been able to achieve. I don't think any PN person other than us have gone through the PM technology using the tools that we develop. I don't think you can upgrade standard post-Newtonian to post-Minkowskian, but that's what the EFT can do, and that's what we will do. And I'm going to stop here, and if you have any questions, please ask. Thank you. That's a good, I could keep the X. And if I keep the X, I have to be careful, because then I have more terms. Because then I can have couplings of DI. Well, in principle, I also have the XI. So what am I saying? This center of mass, the motion of center of mass, when I'm expanding here, you see I have DIX. So I have to keep that in my action. And then through the moment relations, I get dot when I integrate by part, so I'm going to get this guy, which is PI, that will also couple to my action. So if I want to be very careful and include everything, including the dot of the center of mass flux, which I could also compute, then I need to keep all of that in my theory. They will contribute, in principle. However, that effect is subleading. It will enter, but at a much higher order, and therefore we can calculate P dot, and in fact, it's not that difficult. But the effect of that P dot in what I'm doing is negligible.
Which order does it enter?
That's a very good question. I don't remember off the top of my mind which order the fact that the P dot moves. It's also, well, this was recently also taken by Luke and also other people. If it's periodic, then you average it away. But if there is a leftover thing, then you have to keep it. And there is apparently a leftover thing. I don't remember when it starts, but there is a leftover thing.
I mean, it should have because of the kick and the final.
Yeah, but if it's a cake that is like your periodic motion.
Yeah, no, of course.
So then periodic if the cake it goes like cos omega t, you just average away, right? So there is a secular, non-secular part that you need to decouple those, right?
But also the choice of origin will.
No, I mean all of this is relative to the center of mass. Of course, the center of mass moves, and if you were, and this I'm going to tell you an example. If you compute in a scattering, I set up my initial state, and if I have recoil, I have to account for that recoil, for sure. Mm-hmm. But for the binary, there's often, I mean, without spin at least, right? There is no preferred direction, right? It's not that, I mean, most of the time, those effects for the binary, as I said, right, they just average, right? So you don't include it. But if you have a scattering, which is not periodic, then you do have a total recoil that you have to take into account. The symmetry is broken if you want, right? With the spin, you also can have recoil.
But also for different masses?
Yeah, you can have for different masses, you can have, yes. But that effect often, okay, I don't remember the PN order. Do you remember, Ricardo, what Luke said about this P? P5. 5?
Yeah, because if you have 1V more than mass, and then it couples to H0I, that also
yeah.
is 1V more. So it should be 1PN more than the
Well, no, what enters there, yes, no, I'm talking about something else. I'm talking about the fact that we are computing everything. Of course, there are 5 PN effects from the fact that the effects that we're computing are in the relative frame, and the relative frame is moving. So there are second-order effects in radiation reaction, and the radiation reaction is 2.5 that you have to take into account relative to the fact that you're not in the initial frame. And then there's your Hamiltonian has the relative part, and then it has a p square. That p square will have dots. This enters a 6 post-Minkowskian order. This is a G6. Now, at which PN order, I forgot the B's, but it enters later, yeah. Now, the other thing that I was saying is that there is a leftover P, the center of mass, which I forgot now, that Luke recently calculated, which has nothing to do with this. It has to do with the fact that I'm assuming that at all points that it's always 0, but it's not 0, and it's an effect there. That it's not that it affects what I'm doing, it's that it affects what the binary is doing, and you have to include it. Right?
For instance, we can calculate the outgoing angular momentum, and
yes.
then, I mean, conversely, the center of mass.
Absolutely, yeah. Those, all the moments. Yeah. And that's why it's important here that these M's are not conserved. These are dots. These are so-called sometimes the Bondi charges. Because otherwise, if this were constant, then you will never radiate. Because if you look at the full theory with everything, right? We have a conserved T mu nu, and that conserved T mu nu will have an M from this guy, plus things like QQ coupled to this, this, da, da, da. And the fact that the T mu nu is conserved means that the dot of this will have to be QQ, and that's precisely the radiation, right? So those M need to move. It's not the same. In fact, when we compute tails, and this is something that I haven't fully understood, we claim that this M is the full M. Obviously, the dot of this M will be a very high order, but it's the M. In the calculation that these people do, for them, this is the ADM mass, which is not our M. So at some point, we don't get the same thing. However, our multiples are not the standard multiples that they use either. So it could be that this is ultimately fixed by something else. But our calculation of the tail is intrinsically different from their calculation of the tail. They claim that this is the ADM mass, as far as I understand. And for us, it's not. So that's an interesting subtlety that it doesn't matter for all practical purposes, but conceptually it's very interesting.
So in Thorne's definition of multiple moments, I think I mean, I might be wrong, but I think the momentum angle, the linear momentum is 0, is set to 0, right? In the center of
I don't remember what
frame.
Thorne did. I don't even think I ever read his paper. But
it's like
I can include this effect, in fact. Everything I'm doing here is assuming that x is 0. I can both. I can include, because this theory is everything. This theory doesn't have to assume that x is fixed. So I can keep these guys and match for the x's and include them everywhere, if that's what you are. Yeah.
I agree at first order, but like if, for instance, you compute some angular momentum flux away from the source, it means that it's moving, and if it's...
Well, m, the energy is also, I mean...
Yeah, of course, but
no, be careful. Point. No, be careful, be careful.
Okay.
Careful, no.
No? Okay.
No. There are two things.
No.
When you have a binary, right?
Yes.
And it's radiating.
Yes.
If you're sitting here, with respect to the center of mass, there is no p dot. All the p dot is the collective motion, which will be like the recoil in the scattering,
yes.
right? The energy will be lost all relative. There will not be recoil energy. Or most of the, I mean, whichever order that maybe, okay, maybe this is not exact, but the way we get these fluxes are all in the relative thing. This is what we use. We don't include any recoil for this, even though this is computed in the relative thing, in the relative frame, okay? The same for the angular momentum, for the relative impulses and so on. Those guys are also lost mostly on the relative frame. It's the recoil, the P, that we cannot get from here. I mean, we can, but we need to add these x's and keep them and include more stuff, right? And then we need to go to our Hamiltonian for the binary, and we have a relative guy, which is what we're computing, and then we have a p squared. And if we start the dots of these guys, will also contribute. And now you have to include. So it gets very tricky at some point, yes. But most of the losses that we have, and I'm thinking also because, okay, it's also the way that you define this in terms of the relative coordinates and so on has to do with the fact that you can write, for example, in the scattering, what the change of the relative momentum is, right? Based on the relative motion, like we do in Newtonian and so on, right? Up to some recoil, right? And to first order in the recoil, so this, for example, it starts at 3 p.m., so you start getting 3 p.m. square effects, so you got 6 p.m. effects that could affect what you're doing, that will enter at higher orders. But if you just, this I think was done by Thibault, if you just compute here, you get, for example, that this formula is accurate, and then the angular momentum formula is similar. But then for the P, you cannot use this because the total delta P relative is 0. Then you have to compute the recoil, which will be how this P changes. For all practical purposes, well, okay, I should take it back. Because there are things that might look conservative from the relative point of view, which are not conservative from the initial frame in which you don't have a recoil. So you can have forces which just produce a kick in the total momentum, but from the relative point of view, you don't lose energy, you don't lose angular momentum, you don't lose momentum. So they can be written as a Hamiltonian, but they do produce a recoil. So that becomes subtle of what do you mean, this is conservative or it's dissipative and whatnot. Right? But in principle, you can calculate everything. There's nothing that prevents you. And in particular, in scattering, this is not an issue. I never go to any center of mass relative. I always compute in the initial frame. And then I can calculate everything. Right? And then I can even calculate the total recoil because I have a dp1 and a dp2, and I sum them up. They're not 0. Oh, I moved. And that's it. The question is like, okay, how do I use this information? Because if I construct a Hamiltonian, obviously there is dissipation. There is an h dot equal flux. Well, what h am I putting there? How I use that for the binary case, in which the recalls are very different. They don't map necessarily into each other, right? So that's another story.
I suggest we stop.
Yes.
But I don't want to interrupt the discussion. But personally, I have to leave. So
No, we can.
stop the recording.
Yeah.